Hello guys, welcome to recitation number 11, and here we have the edge of a hollow cubic box is 0.3 meters. At first, this box is floating in a lake with 1/3 of its height beneath the surface. The walls of the box have a negligible thickness but a real mass. Next, water from a hose is poured in the open top of the box. Which of the following forces should be included in the free body diagram of the box in the lake once it has some water in the box? So since we want the free body diagram, when water is poured in, so we're going to do the weight of the water, the weight of the box, and then when you're in a fluid, we know you have buoyant force acting upwards, trying to keep you out of the fluid. So we don't need Fk, we don't need normal force, we only need Fb, buoyant force, weight of box, and weight of water. Just these three, that's what we need for the problem. Okay, now let's go to the main problem and solve the problem. Initially, what happens is when the box was floating by itself, is that okay? So initially, when the box was floating, the weight of box equals, okay, weight of water displaced. That's what Archimedes' principle tells us. Weight of water displaced. So this is just rho g volume of water displaced. Is that okay? So rho g times volume gives us weight, but volume is rho g height of the box times area. That's a volume, but it's only 1/3 of the box that is inside the water. So 1/3 of the volume of the box is the volume of water that's displaced. 1/3 of the height times the area. Okay, so this is the weight of box. Now when water starts going in, then we're going to have weight of box plus weight of water now equals weight of water displaced. Now we want everything to sink in, so it's going to be rho g, just the height of the whole box times the area. So the whole box is sinking in. Initially only 1/3 of the height was it, but now the whole box wants to sink in, so we want to see the level of water. So we already have weight of box from here, rho g h a over 3. Okay, this is a over 3. Plus weight of water now is rho g. We don't know the height the water is going to be before it sinks, but we'll just call that height x times the same cross-sectional area equals rho g h a. So rho GA will cancel from both sides, rho GA. So I have h over 3 plus x equals h. So x, the height of water, is h minus h over 3, 3h minus h over 3, 2h over 3. So x, the height of water when it floats or when it sinks, is 2 times the height, 0.3, given in the problem, divided by 3. 0.2 meters. That becomes the right answer. So another way of seeing it is, by itself, without any water in it, 1/3 of its volume is sinking in. So it means 1/3 of its weight is sinking in. So by the time you start putting water inside, since the water displaces the same volume, so you need another 2/3 of water to fill the already 1/3 inside to make the whole thing sink. And 2/3 of water inside means you still have 1/3 of water left up. Is that okay? So it's just, you can use that logic, or you can solve it with the Archimedes principle this way. Okay, this way. So this was before water was put in, and this was after the water starts going in. Okay, for this part. And then we substitute this for the weight of the block of the box in here. Weight of water, we don't know the height of water, and then the whole thing sinks, so the whole height sinks. And then we solve for that. Thank you. I'll see you guys for recitation number 12.